Hello friends, welcome to this training session on measurement system analysis for attribute data. Before we begin, let me briefly explain the topics we will cover in this training. We will start by understanding what is attribute data and where it is commonly used. Then we will discuss typical attribute measurement errors and the risk associated with wrong inspection decision. Then we will discuss why attribute MSA is required. We will go step by step through key MSA elements, repeatability, reproducibility, accuracy, overall agreement and the Kappa Coefficient. Finally, we will understand all these concepts using a practical case study. Then we will interpret the results and get the conclusion. By the end of this training, you will be able to confidently evaluate and interpret an attribute MSA study in your organization. Attribute data is a qualitative data. Unlike variable data, where we measure a dimension like length or weight, attribute data classify a part into discrete categories such as OK, not OK, pass, fail, accept, reject, go, no go. In attribute measurement, there is no numerical scale, so the decisions are mostly subjective. Because of this, a strong MSA is required to ensure the consistency of inspections or judgments. In attribute inspection, errors usually occur near the specification limits. When a part is close to the upper or lower limit, inspectors may interpret it differently. The borderline conditions are the biggest source of inconsistency and judgment errors in attribute measurement system. At borderline, operator can say OK part is not OK or not OK part is OK. There are two major types of decision errors in attribute inspection. First, accepting a not OK part as OK. This is called consumer's risk because defective parts reaches the customer. Second, rejecting a good part as not OK. This is producer's risk, which increase scrap, rework and cost. Let's understand the key elements of MSA attribute analysis. The first one is repeatability. Repeatability is within appraisal agreement. Repeatability measures how consistently the same operator gives the same decision when inspecting the same part multiple times. Reproducibility, it is between appraisal agreement. Reproducibility measures whether different operators give the same results for the same part. Accuracy, it is the agreement with standard or reference. Accuracy measures how often inspection decisions match the known truth, that is master or standard. Overall agreement, overall agreement measures the total consistency of the inspection system across all operators and trials. Kappa Coefficient, Kappa measures how much of the observed agreement is real and how much is just due to chance. Now let's understand attribute MSA using a practical case study. We have a part where hole is to be checked by a go no go gauge. So the decisions are only two, OK and not OK. We will have 20 parts. Out of 20, 14 parts are OK. 6 parts are not OK. Out of these 20 parts, we have some parts, those are at boundary conditions. We have 3 operators A, B and C. These 3 operators will check each part 3 times, so 3 repeats. Decision is OK or not OK. So the total decision is 20 parts, 3 operators, 3 times 180 total decisions. We know the standard of 20 parts. For ease of calculation and for ease of working in Excel, we have coded OK as 1 and not OK as 0. 14 parts are OK and 6 parts are not OK. Definitely, we have to give these parts to the operator in a random manner, and at the same time, operator should not be able to see the numbering over the part. We will note down all the 3 trials output of the operator A and mark wrong decisions with respect to the standard, which is shown in red filled color in this example. We will do the same exercise for operator B and operator C. First, we will calculate repeatability, that is within appraisal agreement. We know repeatability is the ability of the same operator to give the same decisions on repeated inspection of the same part. The formula is repeatability percentage is number of parts with the same decision in all 3 trials divided by total number of parts, which is 20 here, multiply by 100. Let's take the repeatability for operator A. By looking at this data, it is clear that operator A has given same decision in all 3 trials for 16 numbers of parts, while for 4 number of parts the decision is not repeatable. So the number of parts with the same decision in all 3 trials are 16. Total number of parts is 20 and multiplying by 100. So the repeatability for A is 80%. Similarly, we will calculate repeatability for B is 80%. Repeatability for C is 85%. Average repeatability or system repeatability is the average of the repeatability of all 3 operators. If the repeatability is more than 90%, we can say it's a very good repeatability. If it is 80 to 89%, we can say it is marginal repeatability. And if it is less than 80%, then we can say it is a poor repeatability. Low repeatability means the operator is unsure, especially near the boundary cases. So most of the repeatability error will happen in the boundary cases. That is why we have kept boundary cases in our 20 part sample. Now let's calculate the reproducibility. It is between appraisal agreement. We will take trial 2 and find out the instances where operator A, operator B and operator C have given the same decision. This is a summary of trial 2. We can see there are the 6 cases where 3 operators have not given the same decision. The formula is reproducibility is equal to number of parts where all operator agrees divided by total parts multiply by 100. We know the number of parts where all operator agrees is 14. Dividing it by 20 multiplying 100, the reproducibility is 70%. The acceptance criteria for reproducibility is same with the repeatability. More than 90% is very good, 80 to 89% is marginal, below 80% is poor. In our case, it's a poor operator to operator agreement as it is 70%. Let's calculate the accuracy now. Accuracy, as we know, is the agreement with standard. Accuracy measures how often inspection decisions match the known truth, that is our master or standard. Let's see, in our data we have total 14 parts with us. So as per standard, total right decision will be 14 parts multiplied by 3 operators and 3 times. So it will be 126. But we have some wrong decisions here and total count is 6. So total OK decisions are 14 multiplied by 3 multiplied by 3, 126. We have OK to not OK decision 6, that is wrong decision. So total OK to OK decision 126 minus 6 is equal to 120, that is our correct decision. Similarly, we have 6 not OK parts. So total not OK decision will be 6 multiplied by 3 is 54. But we have 5 instances where operator calls not OK part as OK. So total not OK decision as per standard are 6 multiplied by 3 is equal to 54. Not OK to OK, 5 wrong decisions we have. And not OK to not OK, 54 minus 5 is equal to 49 correct decisions we have. So total correct decisions are 120 plus 49 is equal to 169. The formula of accuracy is correct decision compared to standard divided by total inspections or total decisions multiply by 100. So we know we have 169 correct decisions. Total decisions are 180. 169 divided by 180 multiplied by 100. So the accuracy is 93.8%. That seems to be a good accuracy, but it does not remove the chance agreement. We will understand about chance agreement while discussing the Kappa coefficient. Overall agreement, it is percentage of decisions where all operators agrees with each other. In this case, standard is not considered. Let's see the total agreement in trial 1. We can see in trial 1, all operators are agreeing to each other. So total agreements are 20 in the trial 1. While in trial 2, there were 14 cases where all 3 operators were agreeing to each other. In trial 3, we can see there are 15 cases where all 3 operators are agreeing to each other. In trial 1, total agreements are 20, trial 2 14, trial 3 15. So total agreement are 20 plus 14 plus 15 is equal to 49. The formula of overall agreement is total agreement divided by total inspections. We know total agreement are 49, total inspection are 60. So overall agreement will come as a 81.7%. Let's calculate the Kappa coefficient for operator A. For operator A, this is the tabulated output for all 3 trials. We can see operator A has called OK as not OK for 2 instances. So there are 2 OK to not OK wrong decisions, and OK to OK decisions are 14 multiplied by 3 minus 2 is equal to 40. So wrong decisions are 2 and correct decisions are 40. Not OK to OK, there are 2 cases. Not OK to not OK. So 6 multiplied by 3 minus 2, total 16 correct decisions are there. We will do the cross tabulations. We need to make such type of table where we have to give OK to OK decisions, OK to not OK decisions, not OK to OK decisions, and not OK to not OK decisions. Green highlighted numbers are correct decisions and red highlighted numbers are wrong decision. We know for operator A, OK to OK are the 40 cases, OK to not OK are the 2 cases, not OK to OK are the 2 cases, and not OK to not OK are the 16 cases. To calculate the Kappa coefficient, we need to calculate the probability observed, which is denoted by PO here, and probability expected, which is denoted by PE here. To calculate PO, we need observed counts. We already have observed counts OK to OK40, OK to not OK2, not OK to OK2 and not OK to not OK16. To calculate PE, we need to fill expected count in these cells. The formula for expected count is CT multiplied by RT divided by total. CT is the column total, RT is the row total. So in this case, we can see column total is 42. Row total is also 42 and complete total is 60. So this will be 42 multiplied by 42 divided by 60. So the value of expected count in this cell is 29.4. Similarly, we have to calculate expected counts for all remaining cells and fill into the table. The formula for Kappa coefficient PO minus PE divided by 1 minus PE. Let's see how to calculate PO and PE. We have prepared this cross tabulation for operator A. The formula for observed probability PO is total correct decisions divided by total decisions. Total correct decisions are 40 and 16 and total decisions are 60. Formula for probability expected PE is total expected correct decisions divided by total decision. The value of expected correct decisions are 29.4 and 5.4. So summing 29.4 and 5.4 and dividing by 60, so PE came as 0.58. So by putting the PO and PE value into the Kappa coefficient formula, we get the Kappa coefficient for the operator A as 0.841. Similarly, we will calculate the same thing for operator B as the number of correct decisions and wrong decisions are same. So we will get the value of KB as 0.841. Similarly, we will calculate the Kappa value for operator C. It came as 0.882. This is the criteria for Kappa coefficient decision making. If the Kappa coefficient is above 0.75, it is called as excellent agreement. System is accepted. 0.40 to 0.75, it is called as moderate agreement. May be accepted depending on the context. Less than 0.40, poor agreement. In our case, KA 0.841, KB 0.841 and KC 0.882. So it's above 0.75, so excellent agreement. Now we will take a conclusion from our data. Repeatability for operator is 80%, operator B is 80%, or operator C is 85%. As per the acceptance criteria, it comes under marginal range. It may be because of ambiguity in inspection criteria, or because of inadequate training, or because of difficulty in interpreting the defect standard. Reproducibility is 70%. So it's a poor reproducibility. It may be because of unclear acceptance criteria, insufficient visual standards, or inadequate calibration among inspectors. Accuracy is 93.8%. It's very good. Overall agreement is 81.7%. So it's in marginal criteria. It may be because of the variability in operator judgments. If we see the Kappa coefficient, so as per the acceptance criteria, all three Kappa coefficient for operator A, operator B and operator C coming very good. So with respect to overall result, we can see we need to calibrate operator to operator decisions. At the same time, as repeatability is also coming in the marginal area, so we need to provide more training to the operator with respect to the boundary condition parts. Please be connected for more such videos on quality tools. Please subscribe my channel and please provide your feedback. Thank you very much.